Okay, so that's the story on the exam. Any comments or questions? Any problems with the exam? Questions, concerns, thoughts? Anybody alive? No. He said, man, we survived that. Now we got one more of Ahern's exams to live through, right? So the final exam, I don't even recall off the top of my head, is coming up. Is it Thursday? Thursday at noon. Okay. That's a week from Thursday. So we've got some material to cover this week, and this is the end of it, believe it or not. It is amazing how fast it goes by. I am planning for today's class to definitely be a shorter class. I'm going to the memorial service for Beth Ray. How many people in here knew Beth Ray, President Ray's wife? She was a wonderful lady. She passed away in about April, I want to say. And so there's a memorial service for her at 4:30 that I'm planning to finish at about 4:30 and then go to. She was very much of a champion of student ideals and for looking out for students. And so I feel that I want to respect her for that, and for that reason I'd like to go to that. So anyway, I'm going to finish by about 4:30 today. That's the plan. So you can get out and enjoy the sun. Boy, what a dead group! God. All right. I wasn't looking for applause. I was just looking for some enthusiasm. Jesus, I mean, I've had things that I've said that were much more exciting, and people kind of go, but nothing. I was just like, okay, maybe I shouldn't finish early. All right. Well, now that you're awake, let's finish up lipids today if we can. If we can't, we'll finish them tomorrow, but we'll do our best. All right. The rest of what we have to talk about with respect to lipids, now you're noisy, instead of starting to try to talk. The rest of what I have to say with respect to lipids is not going to have the detail of what you've seen so far. It's not going to be as detailed as the stuff that I've talked about so far. So there are very general things about lipids, and you'll see that we can start thinking about these in clusters and groups of things and so forth. So one of these things that we talk about is that actually you've seen a little bit of this before, and this is the synthesis of glycerophospholipids, synthesis of fats. The first one that's relevant for us is the synthesis of a fat. So how does one synthesize a fat? You might think that we take glycerol, and then we attach a fatty acid, we attach a fatty acid, we attach a fatty acid, and we've got a fat. And the reality is that that's not the way we make a fat. Interestingly enough, we actually start with phosphatidic acid, and I'm not going to make you responsible for knowing how we get to phosphatidic acid. What is phosphatidic acid? Phosphatidic acid, I'll remind you, is something that has a glycerol backbone. And so if we think of a glycerol is carbon, 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 right? If you look at me, I'll show you how it looks. Carbon, 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 right? And attached to those carbons are fatty acid, phosphate. That's what phosphatidic acid looks like. A fat would be carbon, 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 fatty acid, fatty acid, fatty acid, right? So the only difference between phosphatidic acid and a fat is the fact that phosphatidic acid has a phosphate in that bottom position compared to a fatty acid. It doesn't have a fatty acid, all right? So there's 2 or 3 ways actually for a cell to make phosphatidic acid. We won't worry about that. So why do I show you phosphatidic acid? Well, it turns out that phosphatidic acid is an intermediate in the synthesis of both fat and the glycerophospholipids. Okay. Phosphatidic acid is a type of glycerophospholipid, but we don't really find it as such in membranes. We find it attached to other things, as I'll explain in just a bit. Well, to make a fat, that's currently what we're interested in. We simply take phosphatidic acid, and not too surprisingly, we clip off the phosphate. That leaves us with a molecule called 1,2-diacylglycerol. And all that is carbon, 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 fatty acid, hydroxyl. That's all that is. Okay? To that last hydroxyl, we add a fatty acid, and bam, we've got a fat. Very simple. Okay? So all we did was we took phosphatidic acid, replaced the phosphate with the fatty acid. Okay. If we were to make a glycerophospholipid, like let's say a phosphatide, a phosphatidyl compound, what we would do is we would take phosphatidic acid and then we would attach something to the phosphate. So if we attached a serine to the phosphate, we would have phosphatidyl serine. If we attached a choline to the phosphate, we would have phosphatidyl choline, et cetera, et cetera. So what we see is that phosphatidic acid is a branch point in the synthesis of fats and glycerophospholipids. It's a branch point in the synthesis of fats and glycerophospholipids. Okay, well, here's the synthesis, for example, of phosphatidylethanolamin. All right, there's phosphatidic acid, and you can see there's several gyrations, none of which we're going to particularly worry about, but the end product of this is phosphatidylethanolamin, and what you see is there's the phosphatidic acid part of it right there. That's everything except for the pink area, and the pink area has been what's been added on in these other steps that you're not responsible for. Okay? So that's what's been added on. That makes phosphatidylethanolamin. Okay? There's other ways of making phosphatidylethanolamin, and you can say, why do I care? And I would say the same question. I don't care. Why should you care? You like that one? Okay. And there's another way of making phosphatidyl. Now, one of the reasons I'm not being very picky with this is because there are several ways for making glycerophospholipids. There's no one path. There's several different ways of making the same things. Okay? So why should we memorize each of those ways? It doesn't really serve any purpose, but being aware that there's multiple ways of getting to that same end product is fine as far as I'm concerned. Okay. If we look at the sphingolipids, I'll remind you that sphingolipids look like they are derived from something called sphingosine, which is right here. The starting point for the sphingolipids is interesting. I'm not sure if I mentioned it when I talked about them earlier in the term, but I will say here. Sphingolipids start as palmitic acid and serine. The palmitic acid is in the form of a palmitoyl-CoA, that is, the palmitic acid is attached to a CoA. Serine gets joined to it, and it makes a compound that gets rearranged to make something called sphingosine. That's what gives these guys their names. So the starting materials are palmitoyl-CoA and serine. Then we've made a sphingosine, which is a starting material for making sphingolipids. Okay? If we take and we add a fatty acid, see here's a fatty acid coming in the form of an acyl-CoA. If we take a fatty acid and we attach it to that amine, we make something called a ceramide. A ceramide. So I take sphingosine, I add a fatty acid to it, I make a ceramide. There's your take-home message. Sphingosine, add a fatty acid, I make a ceramide. That ceramide then, if I take and I add onto this hydroxyl at the bottom a variety of different sugars, I can make other things. Okay? So for example, if I attach a phosphate down here, instead of a sugar, I said sugars, but sugars are one thing I can add. If I add a phosphate down here, I make something called sphingomyelin. Sphingomyelin, I've mentioned before, that is a compound that is, actually it's a phosphate and choline, but that's immaterial for the moment. This sphingomyelin is an important constituent of neural membranes, as we've talked about before. More importantly than sphingomyelin, and by the way, sphingomyelin is an unusual sphingolipid in that it has phosphate. All right? Most of the sphingolipids do not contain phosphate. That's one of the ways in which they differ from the glycerophospholipids. Sphingomyelin is the only one that we talk about here that has phosphate in it. More commonly, instead of adding a phosphate and something else to that hydroxyl, we add either a single sugar, in which case we make a cerebroside, or we add several sugars to make a more complex mixture, and that is what makes a ganglioside. Okay? And we've sort of talked about these before during the general structural features about sphingolipids that I talked about back earlier. Okay. Well, cholesterol is the one I'm going to spend the most time talking about here. And cholesterol is a really interesting compound. Okay? The cholesterol lecture that I give is one that generates probably more questions than about any other lecture. Not the synthesis. The synthesis is kind of boring, to be honest with you. But it generates more questions because people are very interested about cholesterol in the body. We talk about how cholesterol affects human health. It's related to heart attacks and so forth. Cholesterol, as I probably have mentioned to you in class before, there are 5 Nobel Prizes that have been awarded for people studying cholesterol, and we still don't know how all the significance of cholesterol. It's a very, very interesting and important compound. Cholesterol is important in another sense in that the entire cholesterol molecule, and this is a schematic structure of the cholesterol molecule, the entire cholesterol molecule excuse me, can be made starting with acetyl-CoA. Every single carbon that appears in cholesterol comes from acetyl-CoA. So as you look at the figure that you see on the screen, the C stands for the carboxyl part of the acetate, or the acetyl-CoA, and the M stands for the methyl part. Now, no, you're not going to draw this. That's not what's important. But you can see on here that every single one of those carbons that appears in cholesterol can be accounted for and made starting with an acetyl-CoA. Well, we are going to go through the synthesis, and it's not going to be too bad. All right. First part's going to be a little more complicated, but it's not bad. All right. To make cholesterol, we need to start with 3 acetyl-CoAs. Okay. Now, you might remember when I talked about ketone body synthesis, I said that there was a part that branched off and made cholesterol. So today we're going to follow that part that makes cholesterol. When we were talking about ketone body synthesis, we started with 3 acetyl-CoAs. And we made a molecule called HMG-CoA. HMG-CoA is something I want you to remember in the synthesis of both cholesterol and of the ketone bodies. It's a branch point. Branch points in biochemistry are very important things because they can go into multiple compounds. So today we're going to follow HMG-CoA going from HMG-CoA into cholesterol instead of going to ketone bodies. Okay. Well, if we look at this right here, all right, so I started with 3 of these acetyl-CoAs. I made an HMG-CoA, and HMG-CoA isn't even shown on here, all right? When HMG-CoA gets reduced, it makes a compound called mevalonate. And there's an enzyme that catalyzes the conversion of HMG-CoA into mevalonate. It's a very important enzyme in cholesterol metabolism. It's called HMG-CoA reductase. That enzyme is very important because it's a target of many cholesterol-reducing drugs. But before I tell you about the drugs, I need to tell you more about what HMG-CoA reductase does in the cell. HMG-CoA reductase is a great example of an enzyme that's inhibited by feedback inhibition. Anybody remember what feedback inhibition is? Okay, you're getting close. Anybody else? Feedback inhibition. Yes, back there. Feedback inhibition occurs when the last molecule of a pathway, all right, inhibits one of the early enzymes in the pathway. Okay? So, I'm telling you now that HMG-CoA reductase is inhibited by feedback inhibition. That actually works pretty well because when we start getting too much of a product, we don't want to continue synthesis going on, right? We want to stop it. It turns out we want to stop it for a very good reason, all right? Look at this thing down here that says many steps. Okay? Many steps involves over 20 steps to go from squalene to cholesterol. And many of those steps require energy. Okay? If the cell doesn't have a way of shutting things off early, what's going to happen is those steps are going to be wasting a lot of energy on products that the cell has no use for. So feedback inhibition of HMG-CoA reductase turns out to be very, very important. Now, given what I've told you, what do you suppose is the thing that feeds back and inhibits the enzyme? Cholesterol. Cholesterol in your cells inhibits HMG-CoA reductase. Now you might say, well, why, if I have a feedback inhibition for this reaction, do people have high cholesterol? Okay? Well, it turns out that the cholesterol in your body is there from three sources. One is by the synthetic pathway that we see right here. The second is from what we eat. A third is from what we have in storage. Our body stores cholesterol and then can release it as appropriate or as necessary. Okay? Now, if you go to the doctor and the doctor says you have high cholesterol, the first thing they're going to do is probably not put you on drugs. They're going to probably get you to try to reduce your intake and reduce the intake of substances that are thought to increase the concentration or the synthesis of cholesterol. Okay? If by managing your diet you can't control your level of cholesterol, then the doctor is going to start looking at medications that will stop the synthesis of cholesterol. Okay? Because remember, you've got three components: what you're eating, what you're synthesizing, and what you have in storage. If you can knock down what you're eating, that can be of help to you. Okay? There's a class of compounds called statins, S-T-A-T-I-N. And they're a class. There's several of them that are drugs that are used to treat cholesterol. They resemble HMG-CoA. So they are competitive inhibitors of HMG-CoA reductase. Meaning they can stop the enzyme from functioning, they can stop the synthesis of cholesterol. And they're very effective. They're very effective at knocking down the synthesis of cholesterol. Everybody with me? Anybody awake? This is a very unusual group today. Quiet at times, loud at other times. All right. I'll take your silence to mean that you're thinking very hard about this. All right? Okay. Well, let's follow the synthetic pathway. All right? Mevalonate has 6 carbons in it. Okay? There's a decarboxylation of mevalonate that occurs, and when that decarboxylation occurs, it creates a 5-carbon molecule. There's actually a couple of different 5-carbon molecules, and those together collectively are called isoprenes. Right? So the category of 5-carbon molecules used to make cholesterol, that category is called isoprenes. Okay? So there are specifically 2 of them. I could give you the names, but then you would have to memorize the names. This is... Oh, hell, one of them is isopentyl pyrophosphate, and the other is dimethyl allopyrophosphate. That's true. That's the names of them, but I'm not going to make you memorize them. Okay. But they are isoprenes. They're very similar in structure to each other, and they go together like building blocks. So I like to think of them as 5-carbon building blocks. If I take 2 isoprenes and I put them together, I make a 10-carbon compound because 5 plus 5 is 10. And that 10-carbon compound, I think you should know the name of. It's called geranyl pyrophosphate. Geranyl, G-E-R-A-N-Y-L, pyrophosphate. That gives me 10 carbons. If I add another one of the isoprenes to that, I make something that has 15 carbons. And that's something that you should know. It's called farnesyl pyrophosphate, F-A-R-N-E-S-Y-L. Farnesyl pyrophosphate. Okay? So you can see we're just building like building blocks. If we take 2 of the farnesyl pyrophosphates and stick them together, well, you can do the math. We're going to have something that's got 30 carbons, and there's our 30-carbon molecule right there, squalene. Now, since we started with everything being carbons from acetyl-CoA, everything that's in here has a carbon from one of the acetyl-CoAs. Okay? Now, as this thing says, there's many steps. There's actually over 20 steps to go from this, what I call linear molecule, to this cyclic molecule. Okay? The very first step in going from squalene creates something that looks very much like cholesterol. It has ring, 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 ring. The only difference is how the rings are decorated with the different carbons that are there. It might look like it's a very trivial thing to go from that very first carbon, to that very first structure, to cholesterol, but that alone is 19 steps. When I was a graduate student, back in the dark ages, before the wheel was invented, when I was a graduate, before the pipette man was invented, when I was a graduate student back working on my master's degree, I had to memorize every damn one of those 19 steps. Yeah, it was a pain. It was a real pain, and you know what, okay? So one time I actually knew all those steps. I don't know those steps anymore, but needless to say, it's a lot of, and there's a lot of energy that's involved in that. So if the cell can avoid making all this energy for something it doesn't need, it will have that. And that's why the feedback inhibition of HMG-CoA reductase here is very, very important. Okay. There's some of the individual reactions. You're not responsible for that. It just shows you how you... There's HMG-CoA right there. There's the reductase right there. Okay? You're not responsible for the structures. Okay? There's the synthesis of one of the 5-carbon molecules, isopentenyl pyrophosphate. There's the other dimethyl allopyrophosphate. And here they get joined to make, actually this is a bad figure because it shows them making 15. It makes a 10 before it makes a 15. And last but not least, this shows, here's that squalene. And you can see it gets rearranged, and it makes something called lanosterol, which I'm not going to hold you responsible for. It makes something called lanosterol that looks very much like that cholesterol did. Okay? So it has the basic ring structure that cholesterol does, but there's cholesterol and there's lanosterol. Okay. So again, the metabolic pathways are not logical. They're not in any coordinated fashion, but they work, and that's why we work with them. The statins, as I said, are a class of compounds that inhibit HMG-CoA reductase. Okay? They inhibit HMG-CoA reductase, and there are several related compounds. Each of these compounds resembles, okay, actually I said HMG-CoA, it doesn't resemble HMG-CoA. Now I see my figure and reminding myself of this. It resembles mevalonate. Okay? So there's mevalonate, there is a statin. They look very much like that. Okay. Scratch the fact they look like HMG-CoA. They don't. All right. But that's what they resemble, and that is allowing the enzyme to be inhibited. Okay, and back up. I'm really doing bad today. This is not mevalonate. This is mevinolinic acid. This part resembles the mevalonate. My mind hasn't adjusted to being here. Yes? Do these drugs inhibit hormone production? Very good question. As a matter of fact, they can, but hormone production is going to be affected by cholesterol levels. By lowering cholesterol levels, they can affect hormone production as such, but hormones are a relatively small part of the cholesterol metabolism, so I don't know that there's a significant impact on that, but they could, yeah. One of the things that people have wondered about is if you overdose somebody with these drugs, and can you lower the cholesterol levels too low to be dangerous? This is, by the way, I'm not recommending this, but I have read that they have tried in several cases to see if there are dangers or problems associated with very low cholesterol levels as a result of inhibiting synthesis. And so far, I haven't heard of anything associated with that. So it's not something that appears to be a big factor, which is a little surprising considering that cholesterol is used to synthesize hormones, which is considering that cholesterol is very abundant in brain, and cholesterol is important for membranes. It may just be that we walk around with too much cholesterol in the first place. So, okay. All right. Now, Now, there's a couple things made from cholesterol that are important. One is the bile acids. The bile acids are very important for digestion. Okay? And to make them, we start with cholesterol, and then we do something to make them more polar. So here is cholate. You can see it's had a carboxyl attached to the end. Here's glycocholate. It's had a glycine attached to the end of the cholate. There are numerous others. What these all have in common is a very nonpolar part and a polar part. And if you think about it, those are the characteristics of a soap or a detergent. And soap and detergent can emulsify. That helps. That's why you wash your hands with soap, so that you can get the grease that's not water-soluble to become water-soluble. Bile acids are very important in solubilizing fat in digestion. Very important for solubilizing fat in digestion. Okay? So I'm not going to have a chance to talk about it today, but I will talk about that later, and that's a very important consideration of those. The other compounds made from cholesterol that are important include the steroid hormones. So that's what, I can't remember your last name, damn it. Your first name. Haley. What Haley just said. Sorry. I remembered your last name. I couldn't remember your first name. So, sorry. Anyway, what Haley just said. So the steroid hormones, as you can see, look very much like cholesterol. They are made from cholesterol. They include the sex hormones. They include the mineralocorticoids, which are important in balancing minerals like sodium and potassium in your bloodstream. They're important in things like cortisone, which are important for issues of swelling and so forth. As you can see, they come from a common precursor known as pregnenolone, which is made directly from cholesterol. And pregnenolone gives rise to progesterone, which is the pregnancy maintenance hormone. And progesterone gives rise to testosterone, and testosterone gives rise to estradiol. I think I mentioned in class about the aromatase. Have I talked about aromatase before in here or not? Aromatase inhibitors? No. Okay. So let me tell you a brief story about this, and then I'll finish for the day. So progesterone goes to testosterone. If you look at all these different structures that are up here, you'll see that none of them have a benzene ring except for estradiol. Estradiol being the primary female hormone, testosterone being the primary male hormone. The conversion of testosterone into estradiol is catalyzed by an enzyme called aromatase. Okay? It's making an aromatic ring. All right? That's the ring that we see here. All right? It's about the only place in all of biology where an aromatic ring is made directly on the compound. So aromatase is an unusual and interesting enzyme. It turns out that many tumors, okay, are sensitive. That is, means that they're stimulated by the hormone, by the female hormone estrogens. Estradiol being the primary precursor right here. Okay. If you can inhibit the synthesis of the estrogens, in many cases, you can slow or inhibit the growth of tumors that depend upon that. So there are numerous tumors that are stimulated by estrogens. So people with certain types of tumors, including breast cancers and other types of tumors, will have their tumor tested to see if it's estrogen sensitive. If it turns out to be estrogen sensitive, they will put them on inhibitors that stop the synthesis of estradiol, and those inhibitors are known as aromatase inhibitors. They're very effective at stopping certain types of tumors. Not all tumors, of course, are sensitive to that, but some are. And so that stops the production of the estrogens. Okay, that's quite a bit of stuff for a short period of time. Questions about this before I move on? I got one last thing for you. You know what it is. I went to a meeting on education, so I was out of town on Friday. And I went to a meeting on education. One of the sessions I attended was about questions. And it was very interesting and it was very important because it said that questions, people don't think about in the way that they should. That questions can not only lead to answers, but they can lead to other questions. But more importantly, from the perspective of an instructor, a question can be a teaching tool. to make somebody think about something. And so it really made me think a lot about questions. One of the things I learned about questions that was very interesting was that they asked professors, they said, well, do you ask questions in class? And many professors said, yes, they ask questions in class. And they said, well, you know, one of the issues with questions is, do you give your students enough time to think about those questions and answer those questions, or at least consider those questions from their own perspective? And the professor says, oh, yes, we do. And they said, well, how long, on average, when you ask a question in class, do you let students think about that question? And have you heard this? No. Oh. And the professors said, when they took all their answers and they averaged them up, the professors said that on average they gave the class 25 to 30 seconds to think about the answer to that question. Okay? And when they went into the classroom and they timed the professors, I'm not making this up, the average was 3 seconds. And so they said, and I thought of myself in this regard as well, they said things like, the professor will say, okay, any questions? All right, let's move on, right? You've had this happen. So if I do that to you, I want you to say, Kevin. Okay, don't do that, all right? So, because you don't want to stifle people's opportunity to ask you questions as well. Anyway, all right, enough of the educational philosophy. I do have a song that's relevant, and you guys are going to be tired of this melody because I have the same melody as the last 2 times. It's called To Make a Cholesterol. By now you should know the tune. Some things that you can build with acetyl-CoAs are joined together partly thanks to thiolase. They stick together 1, 2, 3, 6 carbons known as HMG, and you're on your way to make a cholesterol. To synthesize a mevalonate in the cell requires reducing HMG-CoA as well. The enzyme is a reductase controlled in allosteric ways when the cell's impelled to make a cholesterol. The mevalonate made in metabolic schemes gets decarboxylated down to isoprenes. They're linked together willy-nilly to build a pp-geranyl in the cell's routines to make a cholesterol. A single pharma cells, but that's not all. The squalene rearranges to lanosterol. From that, there's 19 steps to go before the sterols apropos, which you must recall to make a cholesterol. The regulation of the scheme's complex in ways inhibited by feedback of the reductase. And statins mimic, so they say, the look of HMG-CoA. So we sing their praise and not make cholesterol. All right, see you guys tomorrow.